introduction. My name is Stefan Brenner from TU Braunschweig in Germany, and I'm going to talk about how to make serverless cloud secure. So, to start with a small introduction, I think you will certainly agree that cloud is really still a popular topic, but we can see that there are still very challenging security issues in the cloud, especially if we want to do sensitive data processing in the cloud. And this somewhat hinders the adoption of cloud technologies in general. So we try to make a trusted cloud that allows sensitive data processing and enables processing of sensitive data in the cloud without trusting the provider and by usage of trusted execution technology. So this could allow medical applications, for example, with sensitive patient data. So when we look at trusted execution technologies in general, well, they allow the creation of so-called trusted execution environments. So trusted environments for general purpose code execution, and they offer some hardware-enforced isolation usually. And what is special with the technology that we use is that it adds transparent memory encryption to the trusted environment. So we looked at existing applications and some tried to put complete applications inside such a trusted environment. Well, that sounds appealing because you get your application that you're used to, but you get it trusted now. That is cool, but the problem is that you end up with a large trusted computing base because you will add all that code into your trusted environment and you have to trust it. So on the opposite side, you could also partition an application, extract the business logic that processes sensitive data and put only that into a trusted environment. Well, that reduces the before problem because you will end up with a much smaller trusted computing base, but you have a high effort of porting your application such that it runs in such a way. It's a highly tailored application, requires a lot of insights on the application, and it's a tedious process to partition the application. So, but if we look at current software designs, we can also see that there is some kind of a switch or shift from more monolithic approaches where application is a large chunk of business logic towards more modular architectures. Well, we can see that people start to make smaller components that are more or less independent from each other, that have clearly defined interfaces, that they interfere with each other. And this allows to simplify development in terms of having multiple independent teams that develop independent components of a complete application. So the development process gets simpler and also more independent. And in case of a cloud application, we could even selectively scale only parts of the application. And what is basically following this approach is function as a service or FaaS clouds. In that case, we have really tiny modular components like functions in that case, and they make up the complete application. So we thought, why do we have to partition an application in a tedious process if we can maybe start from an application that's inherently modular? So this is why we tried to focus on function as a service and wanted to make a trusted function as a service platform. So with this introduction, I will now give you a little bit of background on the SGX technology that we used for our application or our platform. Also a quick background on serverless clouds. And then I will show you the trusted serverless platform that we came up with, some facets of it. Of course, and also I will show you an evaluation of it. So the technology that we used, I already mentioned it, is the Intel Software Guard extensions, and this is basically a CPU instruction set extension that allows these secure enclaves to be created. Those are the secure environments in that case. And The special thing about SGX is that those enclaves live in a so-called enclave page cache. This means that the architecture backs the memory pages of an enclave with a special reserved memory range, and to this memory range the CPU applies transparent encryption, also integrity in that case. So this makes an enclave secure, and also we can have multiple enclaves in our application. They're living in user space, and we can have even several of them in the same application as well. So the current problem of SGX is that this EPC is somewhat limited. This is a hardware architectural limit, so currently there's not really a way around that. We have around 90 megabytes of memory for usage of all enclaves on the platform, and even we cannot share any pages between enclaves, right? If two enclaves need the same memory, they have to keep it twice. Yeah, and also SGX provides a feature, we will see that later, to remotely attest an enclave, so we can remotely establish trust into an enclave. So let's have a quick look on serverless cloud. We can basically say that's the follow-up of the evolution of cloud computing, starting with infrastructure as a service, with virtual machines, and now we try to offload more and more tasks to the cloud providers. So the users of the cloud don't have to do that much maintenance anymore, and function as a service is just the last step of the evolution here, because we only provide single standalone functions here. And in this talk, for simplicity, I will just call them lambdas, because this has the name that Amazon gave them. Yeah, and what's cool is that we get a very fine-grained accounting. Even you don't have to pay at all if a lambda is not called. So these are some of the benefits that make functions as a service interesting. Okay, so after the background, I will now go a little bit into the platform that we designed. So basically, we want to be able to execute a lambda inside an enclave. And of course, we are in a cloud setting, we have multiple tenants. We need to be able to execute multiple lambdas in parallel. And also we have to be able to isolate them from each other, because one tenant might not be able or allowed to see the data of another tenant, right? So for this purpose, we had to find a suitable programming language, and also we needed to find a way to allow lambdas to use their own libraries, because a lambda will not really be able to do much without any libraries, right? You will certainly agree here. But also we had to keep in mind that we have this limited memory range of the EPC of SGX, so we cannot really have a very large platform inside our enclave, because if we exceed that limit, I forgot to mention that, we're not exactly limited to 90 megabytes, but we want to keep in that range, because otherwise we have to do very expensive paging to normal memory. It's possible, but it's really slow. Also, we couldn't just do like 1,000 enclaves, because we cannot share pages between enclaves. So we will end up with the same libraries in the EPC again and again, and this also works against our limitation here. And finally, we want to, of course, keep security in mind, and for that purpose we want to keep the trusted computing base as small as possible, because having less code in the enclave means we have less code to trust and also less probability for exploitable software vulnerabilities. Yeah, and finally, this all doesn't make any sense if we cannot establish trust into a lambda remotely, right? Because we're executing that in the cloud, and the cloud can claim it's trusted, but we have to have a proof somewhat, so we can really trust that enclave with our sensitive data. So first we needed to find the most suitable programming language environment for that. So essentially with SGX we would like to go for native lambdas, meaning native code compiled to a binary and execute that inside an enclave. Because in that case, we have a really small piece of code that we execute, very low TCB, right? So, but we end up with multiple lambdas in our cloud, right? So we have to make multiple enclaves, each with its own lambda, and that's good in terms of TCB because it's really small. But because we cannot share any code here, so we really exceed the available memory very quickly. So the other opposite is to have one single enclave and have multiple native lambdas inside it. Well, that's good because we can now share some libraries, but we need to isolate that code inside the enclave from other lambdas, right? And this is the problem of native code isolation. So we need to have some native code sandbox inside the enclave, and that also adds complexity and trusted code base. So this is why we also looked into two different interpreted languages. Those are also the most popular ones for serverless cloud. So a lot of lambdas are already written in those languages. And there was, of course, Python, for example. So if we assume we had Python lambdas, then we can have one interpreter in the enclave and share it between multiple lambdas. So this is good. We can have only one interpreter and maybe be below our EPC limitation. But the problem is that the C Python interpreter, at least, is really large. It's like a million lines of code, right? And also, a lot of Python libraries depend on native components inside their libraries. So we end up with the same problem as with native lambdas, again, because their libraries depend on native components. So, and this is a bit different in JavaScript, right? Because JavaScript originates from browsers, and there used to be standalone applications in general. They don't have many libraries and environment and stuff. So this is why we have a lot of libraries here that are possible in pure JavaScript, and this is why we looked into JavaScript here. And we chose two different interpreters. We have been looking in others as well. First of all, the Duct Tape interpreter is really a good fit because it's a very small interpreter. So it has a very low trusted computing base. If we put it into an enclave, and just same as Python, we can now share the interpreter because we're running it once inside one enclave. Also, we looked into V8 because we wanted to know how fast we could get with a, let's say a bit larger interpreter. So we implemented our platform with those two interpreters and compared their result. You will see the results in the evaluation. So we somehow ended up with this architecture, and as I said, we placed the JavaScript engine inside the enclave, and the idea is to have only one enclave, or at least a low number of enclaves, and load several lambdas inside it from an outside untrusted lambda store. So our lambdas are packed together with their JavaScript-based libraries into a bundle, which is signed and uploaded to our lambda store somewhere in the cloud. And once a user issues a request, then our platform will load the lambda code from outside and place it inside a sandbox inside the enclave. And that sandbox is called a context in Duct Tape, or in V8 it's called a isolate. So it provides a isolation of the JavaScript code that is executed. So we can make sure that these two lambdas do not see the resources of others. So basically we had the goal in mind to even allow lambdas from different customers inside the same enclave, right? And as the code is pure JavaScript, we can be pretty sure that the lambdas cannot access any resources of other contexts because the engine is targeting to isolate that from each other. So this is how we are able to execute JavaScript-based lambdas inside our enclaves. But we need to find a way how to establish trust from the outside, right? And this is how this works. So the idea is now that our platform loads the Lambda just as described before. And once it's inside the enclave, then the attester will attest that enclave. And the attester in that case is the Lambda provider that writes the Lambda and provides its service to customers. So, well, it could be the same as the user also. It doesn't matter if the user is a different person or not. Nevertheless, the Lambda provider that wrote the Lambda will first attest the platform itself, the generic enclave, independently from the Lambdas that are executed inside. And once that's done, once he can trust the platform, he can ask it for a verification of the Lambda running inside it. And once he has established trust into that Lambda, then he will provide a TLS session key. No, not a session key, but the private key. So by this, the Lambda gets access to a key that it can use to establish TLS sessions with the users that sending requests to a Lambda. And the users get an implicit attestation because they can be sure, well, they have to trust the Lambda provider, of course, but they can be sure that the Lambda has only access to the TLS key once it's been attested by the provider. So by this, the users will see from a valid TLS connection that the Lambda platform and the hardware and the JavaScript code inside is all trustworthy. Okay, so I will now show you the results of our evaluation. So what we did is we had multiple clients that issued requests to our platform via TLS. And then we measured the trusted code base, also the throughput, and how much memory we will be using. So you get a very clear picture for why we choose the Duct Tape interpreter first, because really that's a very small interpreter, like only less than 200,000 lines of code, opposed to the really large Google V8. So the interpreter itself is even 7 times larger than Duct Tape. However, if you look at the performance, you get the opposite picture. So we have now 3 bars here for 5 different Lambda codes. So 5 different scripts, basically. Echo is basically doing nothing in JavaScript. So that's the plain platform overhead. And then we have 3 bars for each measurement. The baseline in that case is somewhat similar to what commercial function clouds will offer. So basically that's a Node or V8 based application running without any security on bare hardware. So this is basically V8 without anything. And then we have secure Duct Tape and secure Google V8. And this is both the interpreter running with our platform inside the enclave. So you can now see that the Duct Tape is really lightweight when it comes to doing nothing, right? But that doesn't make much sense. So if we do more complex workflows, and the last 2 are actually extracted from the JavaScript Jetstream benchmark, so we can see that V8 outperforms Duct Tape by far even. So considering the last 3 workloads in particular, which are more or less realistic, we can see that V8 is like 15, 16 times faster. And comparing it to the baseline, so comparing how fast secure V8 is versus the unsecure V8 version, or current realistic function clouds, we can see that we can go up to like 50% of the throughput. Case of Duct Tape, this is a little bit of an unfair comparison because we're comparing secure Duct Tape versus unsecure V8. Okay, so finally, looking at the memory, I've been talking about that EPC limitation a lot. So we wanted to see if we can keep below our threshold of memory, right? You might assume that Google V8 is extremely large and exceeding like this little 90 megabytes very quickly, but unfortunately, fortunately, it's really not that bad because we measured the working set memory footprint of our platform, and we can see that we can stay, in most cases, below that limitation here. And the x-axis in that case is basically the number of parallel contexts that we have inside our enclave. So you can consider it like 10 parallel sandboxes inside one enclave, right? So in this measurement, it's all the same lambda, and this makes even sense because in multi-core architectures, it makes sense to have the same lambda context multiple times inside the enclave because to use the multi-core capabilities. So, yeah, basically this shows how we could run in the multi-core architecture multiple contexts at the same time, and still, because of, we can share the memory, we can keep below that memory limit. But more details on that scheduling is provided in the paper, like how we decide when and how many contexts we create for a Lambda to keep up with the performance requirements. Okay, so to conclude the talk, I have now shown you our SGX-based Lambda execution platform that executes JavaScript-based Lambdas, and you could see that Duct Tape interpreter is very slow compared to Google V8, but instead it uses a lot less memory. I forgot to say that it's using 40% less memory, and also it has a really significantly lower trusted computing base. So with this, we put a price tag for security in a function cloud because we can more or less transparently enable security. So this concludes my talk. Thanks for your attention and taking your questions.
Any questions?
Yes.
Comment, you're basically standing on the top of SGX as a secure platform, which is not. It's already known that it's reachable for speculative attacks like fraudulent or etc.
Yes, we have seen that there are these hardware vulnerabilities, and I'm afraid they're not the last ones that we will experience. We also had new ones just recently, but we can also see that Intel provides microcode updates for that. So it's two attack vectors for the same security goals, that's right, but also Intel has to work on that, I believe. I mean, for our platform, we can.
Intel made a big step with SGX, but it's not yet secure. Then it's an architectural fault.
Yeah, it's not certainly not perfect. Yes, but if there is more demand for security, in our case, you could only have lambdas from the same provider inside one enclave, and then make a second enclave for a different provider. So this will further increase the security levels, and you can also use process level isolation between the enclaves if you have them in different processes, right? So this will give you a lot stronger isolation if wanted, but then you lose a little bit of the memory sharing capabilities, of course.
Did you test in your own lab or you use the public cloud?
We tested that on our own SGX machines. So the baseline is oriented on realistic clouds, so it's V8, of course, like all people do V8 because it's so fast. Yeah.
Any other questions? So maybe while Bodan is setting up, just if you remove the 90 megabyte limitation on the ECB, would you go this way? I mean, is there any other reason for working with the
security? Clearly, I mean, you still want to have the smallest possible trusted computing base, because then if you keep it small enough, you could even go for formal verification if you want.
But actually, so putting the runtime inside the enclave, would that be an approach you would still consider if you remove the 90 megabyte
Well, it
limitation?
depends. I mean, how would you execute JavaScript without putting the runtime inside? I'm not exactly sure.
Yeah, I guess you can put a single runtime per each enclave. That's per each lambda. That would.
Yeah, well, that's already possible right now. I mean, it just scales the problem, right? It's still the same problem, but it scales.
Okay.
Yeah.
Thank you.